Hey, what's up, guys? Okay, so today I want to talk about a very cute decomposition called polar decomposition. Basically, it's like a very small topic in linear algebra that but seldom people will talk about it. But I think it's very cute. So this is called polar decomposition. Okay, so in the linear algebra, there are many kinds of decomposition like LU decomposition or any matrices. Basically, you can write as well similar to the upper triangular matrices. And for some special matrices, you can do the diagonalization, and also you can also do the Jordan form. Okay, but polar decomposition is like a very special one. Oh, by the way, there is a singular value decomposition. Okay, so let's talk about the proof, and also I will explain the detail. Okay, so let's first do this trivial theorem. So given a complex number which is non-zero, the one can write z equals to up, where what u has modulo 1 and the p is positive. Okay, so you can view this as like the trivial version of the polar decomposition. And this proof is very simple because z is a complex number, right? So I can write it as r exponential I theta where r greater than 0. So I can just assign r to be p and u to be exponential I theta. Trivial, okay. And also notice that r is greater than 0, so one can write p to be exponential x for some x greater than 0. For some x is a real number. Okay, and by the way, since the radius of z is unique, so x is unique. Okay. So namely, we have z equals to u to the exponential x. Okay, so we want to say something in the matrix. So in this video, let's first consider all the matrices with and by matrices with complex coefficient. Okay, so let's call it P. Let's consider element P. Where P is first, we need to make sure we need to add some constraint. So the first one is that P is self-adjoint. In the matrix algebra, you can say P is Hermitian. First constraint. The second constraint is that P is positive. Okay, so when I say P is positive, this means that oh, by the way, this is just definition. So I just want to say that if I say P is self-adjoint, means that P is the same as P taker, is basically Hermitian. When I say P is positive, means that for any V, like C to N, this V taker PV or V conjugate PV, conjugate transpose PV will be greater than 0. Okay. So now let's prove. Let's tell you the polar decomposition. So theorem. So in the previous one, the only thing which is non-zero z. So in the matrix, we just need to invertible. Okay, so any matrices A in a general linear group by n invertible matrices can be written as A equals to UP. By the way, this is uniquely. Okay, so A equals to UP, where U is modulus 1 in the non-zero version. So in this version, we need U to be unitary. And the second one is that P is positive. P is positive. Okay. And so this is, you can view this is theorem 1. And then there is another theorem 2. So theorem 2 is that if P is positive, and self-adjoint. Then P can be written as exponential x for some matrix x. For some matrices x, and this is unique, also unique. Okay, and since P is self-adjoint, so one can show obviously x must be self-adjoint. Oh, disappear. So x must be self-adjoint. Okay, so simply speaking, that I want to say is that if P is positive and self-adjoint, then the P can be written as exponential x with uniquely some matrix x and self-adjoint. Okay, so from 1 and 2, well, we have any non-zero matrix A can be written as UP, where this guy is unitary. Unitary. This is unique, and this P is this P can be written as exponential x, and the P is self-adjoint and positive, and the list A is so by 0 and 2 it can be written as exponential x for another self-adjoint matrix x. Okay, so this is like a matrix generalization of this trivial fact in the complex analysis. Okay, so idea is proof. Okay, before we do this, let's talk about some trivial lemma. So hopefully you guys know enough linear algebra. Okay, so let's say Q is a self-adjoint and Q is positive. Then Q has unique, positive, self-adjoint, square roots. Unique, positive, self-adjoint, square roots. Okay, so this is trivial proof. Okay, trivially because Q is Hermitian or self-adjoint, right? So Q can be written as U dagger, where D is this guy's unitary. I can do the diagonalization, and the D is diagonal matrices, and then all these D are greater than or equal to 0. Okay, but this is positive, right? So it must greater than 0. So I can, if I take a square root, then there's unique square roots. Okay, and you might think, oh, this should be plus or minus, but I restrict it to be positive. Okay, so this D, U square root of D, U dagger, this guy, I call square root of Q. So square root of Q is unique. And obviously it's positive because I only pick out the positive roots. And obviously they're self-adjoint. Okay. So one might worry about that. Maybe there's another roots which have this which square will be this Q but different from this. And you can try to prove this by using some analysis, which is simple, because you can prove that if that guy exists, then that guy must has the same eigenspace as this square root of Q, and you can argue that they must be the same. Okay. Okay, so you might need to think about a little bit about this unique, but basically the proving strategy is just what I showed. Okay. Okay. So now we have this theorem, right? Then what we can prove. We can prove the theorem. What? Okay. 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 So the idea is the following. So let's say I suppose A is UP, and I want to find P. Okay, so this is a proof of, this is like the weird proof. So I should say this is a thinking. So since that, let's suppose A equals to UP, then obviously that A dagger is positive. You can prove this trivially. Okay, because this guy is the same as a v. It should be positive for any non-zero v. So I can define p. So this guy is positive and a self-adjoint, right? So I can take the square root. Okay, so I can take the unique square roots. Okay, there are unique square roots by lemma. And then I can define u to be the inverse of this p, right? The inverse of p. Okay, so I can define u to be this. And obviously that I can check u dagger u will be what? Will be least dagger. Okay, so will be a dagger a square minus 1, a dagger a dagger a square minus 1. Okay, so this is u dagger. Okay, because this guy is a self-adjoint, right? So obviously this is, if you let a square a to be y, so you get square root of y inverse, y square root of y inverse. And the things there, these are all commute. You can write down its things is generalizable. So this guy must be identity. Okay. So which makes u to be unitary. Okay, so proof is very simple. Just that p to be a dagger a, take a square roots, and u to be a p inverse. And the rest is just simple exercise. The rest just a simple calculation. Okay, so this proof that one can we have this. Okay, so the remaining part is this uniqueness. Sorry, is this oh, where's this one? Oh, disappear. Oh, so it's the idea is that we need to prove the uniqueness. Okay, so let's say a is up, so it means that p squared is a dagger a. Okay, so which means what? So which means that if there is a decomposition like this, then p squared is always a squared a. But this means that by the lemma, p is unique, right? Because the positive self-adjoint map must be unique. So p is unique, so u is unique. Because u is defined to be a p inverse. Okay, so this shows that uniqueness. Shows the uniqueness. Okay, so yeah, and for the exponential, okay, so first theorem 2, and this p positive matrix can be written exponential x is very simple. You can prove by yourself just using a diagonalization. Okay, so I think I don't have to prove this. So simple idea is that you can write p equals to diagonalization. Then you take the since d is greater than 0, right? So you can take all the exponential. Okay, and they become this, and the exponential is that 1-to-1. It's that 1-to-1 map from all the reals to positive. So exponential x is okay. So this is as 1-1. Okay, so you can prove this is must be unique. Okay. Okay, and there is a preposition. This preposition is also simple but interesting in the legal perspective. Okay, so theorem 1. So for every a, if we only focus on the real number, so previously we worked in a complex number, but in the real number that one can write a equals to r exponential x. So in a complex number, this R will be unitary, but in the real number, this R will be the orthogonal group. And X will be real and symmetric. Okay, so proof is just similar as complex one. Similar as complex one. So this proof is simple. We just restricted every complex number to the real numbers. So unitary will be orthogonal, and the self-adjoint will be real and symmetric. Okay, and the second one is that if you restrict it to S to be a special linear group, basically it means that the determinant of A is 1. Then the 1 can write A equals to U to exponential X, which U is U now is not just unitary, but special unitary. So it's SUN. And the exponential X is the same as X is a self-adjoint. So X exponential X also self-adjoint, but with the condition that trace X is 0. Okay, so proof. I would use think a little bit. But basically, this determinant one is trivial because you can show that you can prove that the determinant of X, the determinant of exponential X is the same of exponential trace X. Okay, you can try to prove this, especially when X is generalizable. Then this proof looks almost trivial. So if this guy is 1, that you should get trace of X equals 0. Okay, and also so obviously that determinant A is U, so times exponential trace X. Okay, so remember that the determinant AB is the same as determinant A times determinant B. So we start from here, then we can arrive here. Okay, now this is guys unitary, right? So okay, so it should be a face, and should be a face. Okay, but this guy must be real. Okay, by the previous one. Okay. Okay, so this guy. So by the okay, so let me just write out. So determinant of U is 1, and then this guy must be real. Okay, so we must have this guy equals to 1, and then this guy must be another 1. Okay. So which makes this trace of X to be 0, and then this guy to be the special unitary. This is due to the well, let me just write carefully. So this is due to the uniqueness of the complex number, right? So remember in the first starting point we talk about the uniqueness of complex number. Uniqueness of the complex number decomposition. So I know that this guy's 1, right? So 1 must be 1 times 1 by this UP. So this guy must be 1, and then this guy must be another 1. So this force determines U to be special linear, and the exponential trace X must be 1. So trace X equals 0. So this is we use the first elementary tool. Okay, so third one is that if we say that A is a special linear group in R, so basically A is real. The determinant A is also 1. Then A can be written as R exponential X, where R is you start from the special linear group, the special unitary groups to the real parts, right? So it's SON. And then this exponential X must be the same. So X is symmetric and real. The trace X is 0. Okay, this proof just combine the 1 and 2. Okay, I think this is all the discussion of this property decomposition. So proof is simple once you know this lemma, and the rest is simple calculation. Okay, so see you guys next videos.